All right, good morning, ladies and gentlemen. Welcome back to your favorite class. Couple of announcements for the course. First, this is like the last week. Today will be like the last lecture with this like intense math that we've kind of been doing for a while. So I know it's kind of been monotonous. It's been a lot of, complicated matrix math and summations and integrations, and man, my head hurts. But we're nearing the end. This will be the last day where we have that sort of discussion. And lecture from here on out will be a lot more about fun stuff. Okay, so uh, with that, I'll say that I have one last homework for you based on the stuff that we're going to talk about today, and it is one problem. Okay, so you have one more tough math problem to do in MATLAB, and then the rest of this class is fun stuff. Okay, so you've made it a long way. All right, one more little push that I need from you, and that homework I posted on Blackboard. It's on laminate failure theory, which is the topic today. Will be due on Wednesday. Okay. Reminder that your first exam is on Friday. Okay. So this is how this week is going to go. I'll have lecture today on laminate failure theory. So one day on laminate failure theory, which is a little bit heartbreaking because we could probably talk about laminate failure theory for a long time. But yeah, one day on laminate failure theory. And then on Wednesday, we'll do a review for the exam. And then on Friday will be the midterm for the course. So I don't want to talk about the midterm here in this forum because not everybody comes to, the live synchronous lectures and not everybody listens to YouTube. So I'll send an email out later today with all the information regarding the exam. So it'll be things like how I want you to orient your laptop, what things are available to you, what the format of the exam generally will be. The format's going to be very similar to exams I've had in the past, a couple short answer questions, like 1 or 2 workout questions, that kind of thing. Okay, so that's what we sort of got going on this week. All right, I will post like an exam study guide also later today, so look for a lot of that information coming out today. Okay, that's what we got going on this week. Any kind of questions on what's happening this week? Anything in the chat? Anything at all? All right. If not, then let's move on with material. And so the material we're going to discuss today is sort of, like I said, the last kind of heavy math portion of the class that we're going to talk about, and that is laminate failure theory. So we've done lamina failure theory in the past, talking about things like how much load can I handle in the one direction before a lamina fails? How much load can I handle in the two direction, right? So these things and these words like longitudinal tensile failure, longitudinal compressive failure, transverse tensile, transverse compressive failure, and shear failure, right? So these are all failure mechanisms we talked about in ME429. Okay, now we're going to look at laminate failure theory. So if you have many stacks of these individual lamina on top of each other and you load this whole unit, how is it going to fail and how can we predict that? And man, I'll tell you right now, laminate failure is complicated. Holy. All right, I want to show a picture that kind of shows some data of very simplistic laminate, like a 0-90-degree laminate that's being loaded and that will fail. And it'll give you some inclination or some hint on to how these lamina fail and how we're going to maybe attack this problem today. Okay, so first thing I want to do is I'm going to share my screen and show up here at the top laminate failure theory. I really particularly like this graph here. Okay, so what you're looking at here, this is a stress strain curve for a 0-94 symmetric laminate. Okay, so 1 0 layer on the outside, 8 90 layers in the middle, and 1 0 layer on the outside. And this thing is just kind of pulled in tension along this x direction. Okay, so this sort of signifies the complications and everything that goes along with laminate failure theory in my mind. Okay, so initially it's loaded up with some laminate stiffness that we know how to calculate now, something like E bar X, which we know how to calculate from lecture number 2. And at some point, because this thing is being loaded, there's going to be failure of some of the layers before others. Okay, and in this particular example, the 90-degree layers fail before the 0-degree layers. So this thing is loaded, this thing is loaded, this thing is loaded. There's certain strains in those certain layers, and that causes those 90-degree layers to fail. And that's what you see around this point here. We start to see kind of this jagged pattern in the load versus displacement. All right, so this is sort of indicating to us that these 90-degree layers are progressively failing in kind of a slow manner, right? So these transverse cracks are forming, and we sort of see that in this image here. It's for us to be like this, these black portions of the composite here are like the 90-degree layers that have failed, right? Now, after those 90-degree layers have failed, excuse me, coronavirus, oh God, no, just kidding. After those 90-degree layers have failed, the composite can still take some load and hold some load, and just now has a modified stiffness where we basically discounted any effect from the 90-degree layer, and this lamina still holds and carries load. Okay, so it still holds those 0-degree layers. Eventually, if this went up and up and up, eventually it would suddenly fail catastrophically, and the 0-degree layers would also fail. But the point is that not all layers fail at the same time. It's a much more like progressive sort of idea where one layer fails, then another layer fails, then another layer fails, then the whole thing fails. All right. The most conservative approach would be to say that our laminate has failed when one layer fails. All right. That's the idea of first ply failure, which is the theory that we're going to really dig in on. Okay. There is another laminate failure theory that is the ultimate failure theory, which says that the laminate survives until the very last layer fails. And that is obviously much less conservative, and that is not something that we're going to do today. One, because it's not very safe to consider, okay, I've got this composite, but 50% of the layers have failed, but yeah, it's still good. It's still good. Just, dust it off. It doesn't matter. Those layers are failed. Who cares? It can still hold load. Yeah, I don't like that. Not one bit, I say, not one bit. All right. So that's reason number one why we don't use that ultimate laminate failure theory. And reason number two is that it's much more complicated. So if you think about loading up a composite and then one layer fails, well, you basically have to then continue your analysis with the assumption that there is zero strength and stiffness of that failed layer. So it makes the analysis much more complicated. So we're going to mostly stick with what is known as first ply failure, which is failure of that first layer dictates ultimate failure of the laminate. All right, so it's much more simplistic. All right, one more voiceover and then I'll go to the white pad. Like I said, laminate failure theory, holy cry, complicated. All right, the basic strategy that we're going to employ in this class is given some loads and moments on the structure. All right, so we apply some longitudinal loads, transverse loads. We apply some bending moments or torques to this lamina. What we're going to do is we're going to determine the stress on each lamina that results from those given applied loads and moments. All right, so we know that we can develop, an expression for the strains and the curvatures, and then relate those strains and curvatures to stresses in the individual layers. All right, so we're going to talk about how to do that. Then we're going to apply a failure criteria for that lamina, that one layer. So we calculate what the stress is in that one layer. Then we apply a failure criteria, like pick your favorite. All right, Tsai-Hill, Tsai-Wu, max stress theory, max strain theory, all those theories that we talked about in 429. All right. Then if we find that the stress in layer K has exceeded the amount that would cause failure, we just say that that particular layer no longer holds any load, and we might see if the remaining laminate can hold or not. Okay, it's this idea of, all right, if this layer failed and all of its load transferred to the rest of the laminate, would the laminate hold or would the laminate then fail? All right, so that's kind of the progressive manner in which we work. All right, now why is it complicated? Oh man, is it complicated. All right, reason number one is that the stress in each lamina varies and it's not particularly easy to calculate. So we can make an approximation for like what the strains are and then relate the strains to the stresses. But man, that's a gross simplification. All right. So that's thing number one, is the stress in each particular layer varies, and this is something that we know. Thing number two is that the failure stress of each lamina is going to be different. Okay. If I load a laminate that's 090, okay, that 90-degree layer is going to fail a lot before the 0-degree layer. And it doesn't necessarily mean that it has a higher stress in that layer. But we know that the 90-degree layer just doesn't handle stress and tension across the two direction very easily. Okay, so even though the stress in that 90-degree layer might generally be less, it could still fail earlier than the 0-degree layer. So that's the general idea, is that even though you've calculated stresses in the layers, and you might see one layer that has, oh, that layer doesn't have a lot of stress on it. Well, that stress might just happen to be oriented in the perfect manner for it to fail. All right, so that's another complication. Different lamina fail at different times, and the laminate might survive even if one of the layers fails. All right, and even if a layer fails, it might still contribute to some load carrying capability. So yeah, okay, we have a 90-degree layer that failed at one particular portion, but the remaining bits above and below that failure can still hold a little bit of load. So we make this gross simplification that yes, one layer has failed and we just discount its load carrying capability entirely, but that's not really true. Okay, it does still have some residual ability to carry load and keep our structure sort of intact, though the failure theory that we're going to discuss in the slides to come really says that no, we're just going to say she gone, can't hold it, can't do nothing, she dead. All right. Next, safety factors. Okay, yeah, hard, difficult to incorporate a safety factor. All right. So if you're going to say layer number one fails at 1,000 units, and you want to divide that by 2 to get your safety factor, man, is it 500 units? Boy, I don't know. It's hard to really give like a linear comparison because the failure is not really a linear function. Okay, so hard to incorporate safety factors. All right, then other fail modes we just are not even accounted for. So we know if we load these laminates, there might be other sorts of damage mechanisms that occur, like delaminations between layers. You could have fiber pullout, right? So individual strands being pulled out from each other. The matrix could be showing plasticity, and we're just completely discounting that. So there's a lot of these other things that are generally going on when we load a laminate that this failure theory just doesn't even talk about. It's like, we don't care about that. But the problem there is that a lot of times when you're doing these hand wavy, like, we don't care about that stuff in engineering, you're doing that because your theory in the end is conservative. Okay. And so if you're saying, well, we don't care about that, and anyways, when we discount that, it's making our theory more conservative anyways. In this situation, it's not making our theory more conservative. All right. If we just discount things like delamination and fiber pullout and matrix plasticity, that makes our theory significantly worse because it is less conservative now. Okay. So we really need to think about the limitations of this laminate theory based on kind of the general strategy of, yeah, okay, we're going to calculate what the stress is in this layer, and if it exceeds this value, then it's dead. All right, it's so much more complicated than that, even though we're going to boil it down to like just this really simple concept and idea. All right, so enough chit chat. Let's go to the pad and let's talk about this. All right, so I'm going to flip you over here, and we'll go to the writing pad. All right. All right. So the topic here is laminate failure theory. Okay. And the first thing I want to do is I want to talk about a failure progression. And so if we're thinking about like loading a composite in, longitudinal tension, how is this thing going to sort of like break down and fail? So let's consider a laminate. That would be like a quasi-isotropic. All right, so I'm going to give you here the 0, 90, negative 45, 45, and symmetric. All right, so what you should have in your mind for this particular laminate is, I'm going to do the best I can to sort of like draw this. And I got to cut it in half, and I got to cut it in half, and then I got to cut each one of those in half. Is that right? Yes. Okay. So we have like a 0, 90, negative 45, 45, 45, negative 45, 90, 0. Okay, so this is our laminate. All right, and if this has got like depth into the page here, we're going to be loading this entire laminate sort of in this general orientation. All right, we're going to put some load on here. Let's just call it like NX, or what you might want to call is like sigma bar X. Let's just say that they're kind of like equivalent loading in this direction. All right, and we want to think about like the orientation of how sort of the fibers are moving in each one of those individual particular layers. I'm going to kind of draw the fibers here in blue. So the 90-degree layer, you're going to have your fibers that are kind of like coming across the page like this. So those are what's happening in the 90-degree layers, kind of here. So in those particular layers, the load is directly across the fibers. All right. So the 0-degree layers, we're going to have, your individual fibers in each one of these particular layers. So the fibers are going to kind of be coming in and out of this loading direction, in and out of that page at the 0-degree orientation. All right. So we got all the fibers in the 0 coming out. And the plus minus 45 layers, if we're sort of looking at it head on, there's going to be they're going to actually like look elliptical, the fibers themselves, when we sort of cut them and look through them. But it will have some sort of like elongated, not quite full fiber length, but some sort of like elongated sort of looking fiber. All right, as you cut through it with each one of these fibers, like at a 45-degree angle, they might kind of like look like short fibers at this orientation, if you sort of like want to think of it like that. All right, so the load's not directly across the two direction. The load's not directly in the one direction. It's kind of like at this 45-degree angle, right? So what is the failure progression going to be? So failure progression. Well, what do we know about individual lamina generally? So lamina strengths. We generally know that if I'm in tension, so generally in tension, I know that like F1T is way, way bigger than F2T. Okay, so I can hold a lot more load in the one direction than I can hold in the two direction. Right? And I generally know that F1T will also be way, way more than F6, and F2T is going to be slightly less than F6, usually, if I'm talking about lamina failure theory. So with that idea in mind, we could kind of think about how this guy is generally going to fail, or how the progression of this guy is going to go if we load this, right? So let's think about like a stress strain curve. Looking something like this. So here's like strain in the X, and I'll say the mean strain in X. Here's the mean stress in X. How's this thing going to progress? All right, well, if we look at this guy, originally when we're loading this guy up, it's going to have the modulus of the laminate. So you know how to do and calculate the laminate modulus, right? So figure out what the little a matrix is and use that in your laminate engineering properties calculation. It's something like you did for homework number 1. So this thing is going to load up originally with some stiffness here that is like E bar X. All right. So originally it's just going to load up, load up, load up, load up. Okay. Then sometime later, there will be some failure event in one of the individual layers. Okay. So in this particular laminate, because this load here, this NX, is sort of directed directly across the fibers in like these 90-degree layers, what's going to happen is we anticipate, because those 90-degree layers are so weak in that 2 direction, right, of that particular lamina, we would anticipate those layers kind of failing first. And our theoretical failure would say that both of those layers are going to fail at the same time. And this is just coming from the theory, because there's no preferential reason why one of those 90 layers would fail before the other. So it's more or less they both fail at exactly the same time. So this guy is loading, 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 and ultimately we see some failure that occurs. All right. And at this particular point, I'll say 90-degree layers fail together. All right. Maybe better do that in red. All right. So these 90-degree layers fail together. That's kind of like what the theoretical concept sort of is. Now, in reality, that doesn't actually happen because, yes, these layers are not aligned exactly at 90 degrees. And so maybe the one that is closer to 90 will fail before the one that's slightly misaligned from the 90 degrees. Okay. Maybe one has slightly less volume fraction, so it fails first. Okay. That's practical. All right. This is kind of like still theoretical concepts. All right. So when this like 90-degree layer fails, to relieve like the stress that's on there, the individual layers will fail. But that doesn't necessarily mean that the laminate is completely failed. Yeah, it loses the ability to carry load in those particular layers, but it can persist more or less. So what happens now is the laminate will continue to load up after that 90-degree layer has failed, but will have reduced modulus. It still holds and loads, but at reduced modulus. Okay, and that's only because like the 0 and the plus minus 45 degrees layers are alive. Okay, so those are the only layers that are now kind of like holding. All right, so this guy's going to load up, this guy's going to load up, and then sometime later, another series of those layers in the composite are going to fail. And just from theory or from knowing this from experience, it's going to be the plus minus 45 degree layers will fail. Okay, so now we hit another sort of like failure point where this laminate will again sort of like reduce load. And at this particular point, it's going to be the plus minus 45 layers fail. All right, so there we go. We've again lost a bunch of our load carrying capability, lost a lot of energy associated with those layers holding load. So those of you taking the fracture and fatigue class with Schaefer, hopefully you've talked about the energy of fracture. If not, we're going to talk about it in my class. So that'll be fun also. Those 45-degree layers fail, and the energy associated with those layers and what they've held now is lost. Okay, but let's say that our 0-degree layers, they're tough. All right, they can still persist. So here now, the 0-degree layers load up again with the reduced modulus until ultimately those 0-degree layers fail, and the entire thing fails. All right, so here, finally, the 0-degree layers fail. All right, so that's the general idea there, is that there's this like slow progressive failure where each one of the individual layers kind of fails in sort of a progressive manner. All right, so that's kind of what the theory says, and that's how we're going to base the math in this class. Okay, is that we're going to figure out what the stiffness is of the particular composite, how much load that particular composite can hold before it fails, and then we'll figure out what layer has failed. All right, so that's generally what's going to happen with this sort of stress strain curve. Now, that's kind of like ideal theoretical data, but in actuality, kind of like I showed at the beginning of the lecture, that's not really what happens. So in actuality, what happens is, like I showed before, something that looks like this. Okay, so here's again your actual data. So yeah, why don't I'm going to copy this over to the white pad and I'll talk about it there. This way I can draw on it. Nifty, huh? All right, so here's your actual data. Like I said before, the laminate is going to load up with some initial elastic modulus, E bar X, right? So this is like the elastic modulus of the laminate as a whole. And then at some time later, things are going to start failing. So this is 90-degree layers failing. But unlike kind of what we talked about in theory happens, where like we say they all sort of fail together and just the load plummets, that's not in actuality what really happens. So in actuality, what really happens is the cracking inside of the individual layers sort of progresses in sort of a very progressive kind of way, okay, a little bit at a time. The 90-degree layers aren't just all failing at the same time, but it's very progressive and minor, and you start to see a lot of failures in those layers as we go through until ultimately the layer has kind of failed completely. Okay, so this is like progressive here. Until at this location now here, with its full 90-degree layer failure. Okay, then at that point, now the 0-degree layers take over. All right, so that's the general idea. So there's this, in actuality, this much more progressive type sort of failure. All right, so there's your actual data with a little bit of Dr. Hart marking. Kind of looks like your paper, all that red on there, right? Like when you guys do homeworks. Just kidding, not this quarter. All right, so that's some actual data. Now let's talk about the theory and how the theory actually works. So in this class, we simplify. And what I'll say is that there's really two ways to think about laminate failure theory. To attack laminate failure. And number one is, we'll say that the laminate fails when first layer fails. Okay, we call this first ply failure theory. Okay, so if we like kind of go up to the actual data and we go up to kind of like our theoretical stress strain, then we would say that by first ply failure theory, the laminate would have failed right when this guy starts to first show failure. Okay, so this here would be our first ply failure. All right, that's right when this guy first shows signs of failure. That's right when that 90-degree layer first begins failing. All right, in our sort of like little theoretical stress strain curve, that would be here. All right, there's your first ply failure. Right when that first layer has failed, then we say that the laminate has failed. All right. The other way to look at laminate failure theory is kind of the complete opposite of that, right? So first ply failure is saying, yeah, it's going to fail when that first layer fails. Then our ultimate laminate failure theory is going to say that we fail when the last layer fails. Laminate has failed. Last layer fails. Okay, we call this the ultimate failure theory. Ultimate laminate failure theory. All right. This is the one we're going to do in this class. So we're going to focus on first ply failure theory. Okay. And lucky for you guys, that first ply failure theory is more simplistic. All right. So I'll say is easier. The reason that it's easier is you just look basically at the full laminate and predict only when the first ply has failed. If you wanted to continue on with ultimate laminate failure theory, which is kind of like this second level, what you'd have to do is you'd have to continue on with your laminate analysis, but you'd have to discount whatever layers had previously failed. So you'd be creating an ABD matrix with like zero stiffness for the layer that has failed. That's basically like how the analysis would have to proceed. All right. So that's the general outline there. We're going to stick with number one, mostly because we don't have time to do number two, unfortunately. All right. So enough intro. Let's get down to stuff and brass tacks, as they say. How do we do this? So math methods. All right. Here's the secret. You ready? You already know how to do this. Okay. So I don't have to teach anything new. What I do have to teach you is the process. Okay. Because it is a process. If I think about, I'm going to make a laminate that has a certain stacking sequence made from a certain series of fibers and matrix material. I'm going to load it in this certain way. How can I predict how it's going to fail? There's a very long process there. Okay. You have to think about, what are the fiber properties? What are the lamina properties? How am I going to create my Q matrix? How much is there going to be stress and strain on this guy if I load it a certain way? Then how do I develop the stress and strain in the individual layers to sort of bring in my failure theory? There's a lot there. Okay. So I only really need to teach you the process. Right. So I've created a flow chart that just sort of shows what the process might look like. All right. So let's pivot you over to pivot. Let's pivot you over to the slides. All right. So here is your computational procedure. I'll blow this up. Or I won't blow it up. All right. So here's your general computational procedure. You are going to create a laminate, and we're going to assume that you know properties of that laminate, enough properties to give you what is the capital ABD matrix. Okay. So you know the stacking sequence, you know the constituents of the individual layers, so on and so forth. You should have enough experience now calculating the ABD matrices that you sort of understand how this happens. All right. After calculating the laminate stiffness matrix from ABD, you can get the laminate compliance matrix by inverting that. Okay. So again, you've done a lot of this. All right. Now, I want to go from what are applied loads and moments on my laminate. Okay. So I'm going to apply some loads. I'm going to apply some moments to my laminate. And ultimately, I want to know, what is my safety factor against failure? So that's where we're starting. That's where we're going. So the general process here is, take the applied loads and the applied moments that you know, and using the laminate compliance matrix, we can determine the laminate strains and curvatures in the XY coordinate system. All right, so we have an equation over here for that. That's using the inverse compliance matrix relating the loads and moments to strains and curvatures. All right, so you've done that already. Next, I want to determine what the strain is in layer K. So I want to know, at every single layer inside of the laminate, what is the strain at that particular layer? Okay. Well, it's a combination of the midplane strains and the curvatures. Okay, so the mid-plane strain here is the mid-plane strain of the laminate. So the whole laminate has the same sort of longitudinal strain. And then I have to add to that whatever strain comes about from the curvature at that particular layer. All right, so that is the strain in layer K, approximated with this general function. All right, the farther it is away from the midplane, meaning the farther these values of Z, the more strain that layer will have from the curvature of the laminate. Right, sort of like makes sense. I transfer the strains in the XY coordinate system, the global coordinate system of the laminate, into the principal material coordinates. So if I have a 0-degree layer, then the strain in that layer is the same as the 1-2 strain. All right, but if I have a 45-degree layer, I have to realign my strains into the principal coordinates using my typical transformation matrix T star. All right, so when we're talking about transforming strains, we use the T star matrix. Then from there, if I know the strains in layer K, I can get the stresses in layer K by using the in-plane stiffness matrix Q. So this now will give me my stresses in principal directions, right? So this is stress in layer K in principal coordinates. Then I apply a failure theory. And most commonly, the failure theory that is used in this type of analysis is the Psi-Hill theory. And that's because the Psi-Hill theory is one mathematical theory. It is not like determining the minimum and maximum of many stresses. Computationally, this is much more easy to execute than looking at sigma 1 alone, sigma 2 alone, sigma 6 alone, which you might do for, let's say, the maximum stress theory. Okay, so typically this is the theory that is used because it's sort of the most computationally simplistic. All right, so we get the stresses in the individual layers, and then you apply your lamina failure theory of the individual layer K. Okay, so what that affords you is the safety factor against failure in each individual layer. So for the kth layer, we can calculate a safety factor against the current loading that's on the piece. All right, so it's a long process there, and definitely something you don't want to be doing by hand. Don't want to be doing that by hand, I promise you. All right, so calculate the safety factor in layer K, and then repeat that process here, which is the strain and stresses and safety factors in each layer, over and over and over for every single layer. In the end, you'll have a safety factor for every single layer. And if any one of those safety factors is less than 1, you would predict failure. All right. If none of the safety factors are less than 1, well, then the safety factor for the laminate as a whole is the smallest of all of the safety factors that you have calculated. All right. So that's the process. You already know how to do all of it, right? There's nothing new mathematically I have to teach you. You just have to go and do it. All right. So I have an example problem here. If you want to take a look, we'll maybe talk through it. Okay, we got maybe 5 or so minutes to talk through it. Here is a full example problem. You've got 100 by 100 by 4 millimeter quasi-isotropic laminate loaded biaxially with a certain force. Determine the factor of safety against failure for this laminate. The stacking sequence here is 0, negative 45, 45, 90, 2. Okay, this is not an S down here. This is a 2. So that means 0, negative 45, 45, 90. 0, negative 45, 45, 90. So you're repeating this pattern twice. You're given the in-plane stiffness matrix Q, and you're given failure strengths of the lamina, so the individual layers. So we're going to look at this and see what the factor of safety against failure would be. And then also I ask if you changed it to a symmetric laminate, meaning 0, negative 45, 45, 90 symmetric instead of a 2, how would the safety factor change? All right. So I have a series of MATLAB code here that sort of shows this. This is just initial information. So here, the length of the laminate in X is 100 millimeters. The length of the laminate in Y, 100 millimeters. Total height of the laminate is 4 millimeters. Here's my force vector. This is my stacking sequence. Again, 0, negative 45, 45, 90. Repeated, 0, negative 45, 45, 90. Okay, it's not symmetric. T, this is the thickness of each lamina. Okay, so each individual one layer. And then Z, this is my locations of each one of the individual layers. And by the way, some of you guys creating this Z vector, very suspicious. All right. I've seen like crazy for loops trying to create these Z values. All right. You're going from negative h on 2 to h on 2 with a spacing of t. Like, this is all you really need. All right. Q matrix, and then here are my failure stresses for the lamina. Okay. So now I need to calculate my n and m vectors following my theory. All right. So the loads normalized by the lengths in the individual directions. This is fx on ly. This is fy on lx, and we don't have any across the face loading. Moments, I got no moments. So here I'm creating my 6x1 load moment vector. And here I'm converting to giga so that I can work appropriately with the Q matrix. All right. Continuing, here's my ABD matrices, both the stiffness ABD matrices and the compliance ABD matrices. So you should be very comfortable calculating those at this point. And I calculate the resulting strains and curvatures using this general formula here, where my loads and moments multiplied by the laminate compliance matrix. All right. This is the resulting strains and curvatures of the laminate as a whole. All right. So I have some positive strain in X, some positive strain in Y, a very small amount of negative shear strain. In here, I have resulting curvatures kind of in all three orientations. So I've got curvature in X, I've got curvature in Y, and I've got this torsional curvature kappa XY. All right. Here now we employ that failure analysis for each one of the individual layers. So I'm not going to kind of like dive in on the code here. You can sort of look at the code later if you want. But the idea is that we're looking at failure of each one of the individual layers and iterating through each one of those layers. Okay. So ultimately what I've built here is the safety factor kind of on the left-hand side for each individual layer based on the stacking sequence that I was originally given. Okay. And we see here that this particular lamina, this particular laminate, would fail in the 90-degree lamina on the top of the piece. Okay, so let's kind of talk about maybe why that would be. All right, so this 90-degree layer on the top of the laminate is the most vulnerable. It has the lowest safety factor. So additional strain and stresses on that layer from curvature of the laminate, coupled with the 90-degree orientation being weak, tend it to be the one in the most trouble. So if we thought about like a laminate that had many layers on top of it, and we sort of put this thing in and put some curvature on it and loaded it, if there's a 90-degree layer on the top of there, that guy is really vulnerable. And that's because there's going to be a lot of strain in that layer because he's very far from the midplane. All right. So we know with bending that strains induced on that top layer are very dramatic. Okay. So that's sort of the analysis there. If we replaced the stacking sequence with sort of like 0, negative 45, 90 symmetric instead of the 0, negative 45, 45, 92, we'd have pretty significantly different results. So here the laminate safety factor for the symmetric laminate is 2.8 instead of, you know, what is 1.6. So pretty dramatic shift in the safety factor just from changing the stacking sequence alone. And that's because we've moved the vulnerable 90-degree layer from what was sort of the top of the laminate to the middle of the laminate. Okay, so now we have a lot of our concentrated weak layers in the center where any sort of loads that might come from curvature of this laminate are not as significant. All right, so there you go. That's it for laminate failure theory. You have one problem that I want you to get done by Thursday. Please do your best there. It'll be the last really intense sort of mathematical problem that we have for this class before we get to fun stuff. All right, so fun stuff coming after this test. I know, just buckle in, like one more quarantine week, and then I promise we'll get the good stuff. All right, so that's it for today. Thanks for coming. I'll stick around for a couple of minutes if people have questions.